Okay, so let's start. So today we'll solve four questions from both real and functional analysis. Okay, so let's start. Let me share the screen. Okay, so today we'll solve Gate 2018 question. This is a question from real analysis. It is question number 50. So sin pi x is written in terms of Fourier cosine series a naught plus summation n equals to 1 to infinity n cos n pi x for x between 0 to 1. Then you have to find a0 plus a1 times pi. What will be the value of this? Okay. So this is the NPTEL reference. This you can look into it. Okay. So let's try to solve this one. So sin pi x is written in terms of a0 plus summation n equals to 1 to infinity n cos n pi x for 0 less than x less than 1. We have to find basically a0 and ans are what we have to find, or a1 we will need. So first note that, so let me write, if f is a function with period 2l, then the Fourier cosine series of f becomes, you can write fx equals to c naught by 2 plus summation n equals to 1 to infinity cn cos n pi x by l, where cn's are given by 2 by l integration 0 to l fx cos n pi x by l dx. So this is the, if f is written in terms of Fourier cosine series like this, then the coefficients cn's are given by this formula. So we will use this formula to find the coefficients. So here sin pi x. What is the period of sin pi x? So here note that sine pi x is a function with period 2. Why? As sine pi of x plus 2, if you do sine, you'll get pi x or 2 pi plus pi x. As sine is 2 pi periodic, so it will become sine pi x. So sine pi x is 2 periodic. So therefore here L is become 1. So sine pi x, you can write it C0 by 2 plus summation n equals to 1 to infinity cos L will become 1 means n pi x. And where Cn will be given by 2 because L is 1, 0 to 1. Sine pi x times cos n pi x dx. So these are the coefficients. So therefore, what is the relation with A0 and A1? Oh, sorry, here it will be Cn. So A0 basically from there it is written A0, but here you will get C0 by 2. So A0 is C0 by 2, and what will be A1? A1 will be C1. So let's compute what is C0. So C0 is given by this formula. So n equals to 0, it will be only. So this is for all n bigger than 0. So what will be C0? C0 will be 2, 0 to 1 sine pi x dx. So let's calculate what will be this. If you integrate it, it will get minus 2 by pi cos pi x 0 to 1. So minus 2 by pi cos pi is minus 1 minus 1. So you will get basically 4 by pi. So this is C0. Now let's find what is C1 and what is C1. C1 is 2 integration 0 to 1 sine pi x, and it will be cos pi x n equals to 1 dx. So this you can write, how you can write 2 sine x cos x. You can actually this is 0 to 1 sine 2x, same as sine 2 pi x dx. Now if you integrate, you will get minus 1 by 2 pi cos 2 pi x from 0 to 1. So minus 1 by 2 pi cos 2 pi is 1 minus cos 0 is 1. So therefore this becomes 0. So C1 is 0, C0 is 4 by pi, and A0 is C0 by 2, A1 is C1. So therefore, we get a naught, which is c naught by 2. C naught is 4 by pi, it will be 2 by pi. And a1, which is c1, equals to 0. So therefore what we need to find? We need to find a naught plus a1 times pi. Therefore a naught plus a1 times pi, which is 2 by pi, plus 0 times pi, so it's 2. So the answer is 2. So a naught plus a1 pi is 2. Okay. Okay, any questions or doubt? C naught by if you have any question you can ask. So no doubts. Okay, then we can move to the next question. Okay, so let's move to the next one. Okay, so today we'll solve Gate 2018 question. This is a question from functional analysis. It's question number 48. So let U be a orthonormal set in a Hilbert space H, and let X belongs to Hilbert space H be such that norm of X equals to 2. Then consider the set E is all such U in the capital U such that mod of inner product X with U is bigger than 1 by 4. So this set, then the maximal possible number of elements in E is that you have to find. Okay. So this is the NPTEL reference. This you can look into it. Okay, so let's try to solve this one. So what it is given? It's U be an orthonormal set in Hilbert space H. Okay, and for given x, let x belongs to H, that is script H, such that norm of x equals to 2 is given. Then a set E is defined. It is all such U in capital U such that inner product x U is bigger than 1 by 4. Then you have to find cardinality of E basically. How many points of U it lies inside the set E. Okay, so this type of set, for that we need Bessel inequality to solve this one. So what is Bessel's inequality? So let H be a Hilbert space and let U1, E2 dot 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 be an orthonormal set. In H. So this is an orthonormal set. Then for any x in Hilbert space H, one has so inner product x with EI, I belongs to some index, that index set. So I equals to suppose 1 to n. 1 to infinity. This is less than norm of x square. So this is the Bessel inequality. It's saying that for Hilbert space, given any orthonormal set, not necessarily basis, they may not be basis, means they may not be span the whole of H. For any orthonormal set, for any x in the Hilbert space, if you take the x inner product with all that orthonormal set and sum it, it will be always less than the norm of x square. Yeah, there is generalization, means when this set become orthonormal basis, means complete orthonormal set, then we have Parseval, it become equality in that case, if it is become the orthonormal basis. But here we do not need this. So we want to use this Bessel's inequality to do this one. So U has an orthonormal set. So for as U is an orthonormal set, H. So let U equals to like this, U alpha. Alpha is some over index set. So then by Bessel's inequality, we have what we will get. So summation x inner product U alpha mod square for alpha belongs to the index set. This is less than norm x square. And so for that x, norm x equals to 2, we get left hand side. So E is, you have to find E. In E, how many elements are there? So this alpha belongs to I and U alphas that are in E. So for this it will also be true, U alpha less than norm x square, which is 2 square equals to 4. And for as what is E? E is all such U in U such that norm of x U is bigger than 4. So if you use, but if U is belongs to this capital U, then norm inner product x U with U is bigger than 1 by 4. So use this one. So what you will get? Summation alpha belongs to I and U alpha belongs to E. So this will be 1 by 4 square is less than this. Alpha belongs to I, U alpha belongs to E. Four, right? So what is this side? So it 1 by 16 will come out, and this will be the U alpha in E. It's 1 less than 4. So what is this set? It is all the elements U alpha in E, right? So this will be basically, cardinality of E. So this will be less than 4 times 16, which is 64. Where what is this? Where cardinality of this is the means number of U belongs to U which lies in E. This is the cardinality of E. So we get cardinality of E is so cardinality of E is less than 64. So therefore maximum number of elements in E is 64. Therefore maximum number of elements in E is 64. So therefore this is the answer. So the answer is 64. Okay. Okay, any doubt or any question? Is 64. No question. So let's move to the next one. Okay, so today we'll solve Gate 2018 question. This is a question from functional analysis. It is question number 41. So consider the R3 with the usual inner product, and D is the distance from 1,111 to the subspace, which is spanned by these two vectors, this 110 and 011 of R3. Then you have to find the 3D square, where D is the distance from this point to the subspace. Okay. Okay, so this is the NPTEL reference. This you can look into it. Okay, so let's start solving this one. So on R3, point is given 1, 1, 1. And let's call it the subspace S. So this is the span of 1, 1, 0 and 0, 1, 1. So D is the distance of 1, 1 from that subspace S. So then we have to find 3D square is what? So R3, this is a inner product space, so Hilbert space. So in general, Hilbert space, so finding the point, distance of a point from the subspace, so we get, for that we need the projection of that point onto that subspace, and this will give the distance between that point and the projection of that point to the subspace will give the minimum, so the distance. So you have to find the projection of that point onto the subspace. So let me write that result first. Let H be a Hilbert space. And S be a subspace of H. Let S does not belongs to H. S, and this is the point outside S. Then there exists a unique point x0 such that this norm x minus x0 is the distance of x comma this set S, which is defined to be the infimum of all such x minus y such that y is in this set. Right, so this is the distance, and where this x0 is the projection. This x0 is called the projection of x onto S on that subspace. and there is a formula for this x naught. So P of the projection, how it is generated, of x is x naught. Okay, so we have to find the projection of that point. So for that, so first what you will do, we will first use the Gram-Schmidt orthonormal process to find the orthonormal basis for this subspace S. We will first use Gram-Schmidt orthogonalization. So in the S is 1 1 0 0 1 1. So first take U1 to be this vector 1 1 0. Now next we have to find a vector which is orthogonal to this vector. So this is given by the Gram-Schmidt orthogonalization. So U2. So this will be the 1 1 0. Means no, that vector, other vector 0 1 1 minus the inner product of this vector, means the projection of that vector in the direction of U1. So this is 1 1 0 and orthonormalize this vector 0 1 1 1 1 0 first. And this is 1 1 0 vector. So what we'll do, we'll take this vector, next vector, and we have deleting the component of this 0 1 1 in the direction of 1 1 0. So this is the projection of 0 1 1 in that direction, 1 1 0 direction. Right. So then it will be orthogonal to, then U2 will be orthogonal to U1. So let's compute what this is. So this is 0 1 1. To calculate the inner product, it will be 1 1 by 2 1 1 0. So it will be minus half and 1. So then now orthonormalize it. Now normalize it. So what is the norm of U1? So square root of 1 plus 1, it is 2, and norm of U2, one by 4 plus 1, so it is square root 3 by square root 2. So S is also the span of this tree orthonormal vector. Oh, this is square root 2. 1 by square root 2, 1 1 0. So we are dividing just by the norm of that vector. Square root 2 by square root 3, 0 1 1. So we get that S is the span of these two vectors. So let me call it span of P and Q, where P is this first, where P is this vector 1 by square root 2, 1 1 0, Q is this vector. So in order to find the distance of 1, 1, 1 to this subspace, we need to find the projection of 1, 1, 1 onto S. Let V equals to, I am calling it this 1, 1, 1. Then the projection of V onto S is given by, so it will be the projection of V onto S, it will be V inner product P and P in the direction P plus, that means basically linear combination of the projection of all this V inner product Q in the direction Q. So basically this is P of XB. So P of S110 it will be inner product 1, 1, 0 inner product with that vector P 1 by square root 2 1, 1, 0 plus into that plus inner product 1, 1, 0 inner product square root 2 by square root 3 0, 1, 1. Sorry, I forgot. This vector will be different. This will be that vector U2 minus half, half and 1. This is square root 2 by square root 3 minus half, half 1. Now if you calculate this one, what you will get? This is 1 by 2. So basically you will get, I am writing it just, I am not doing the calculation. You will get first 110 plus 2 by 3 minus half, half and 1. So basically this is the two by 3, 4 by 3 and 2 by 3. So this is the projection of, 1, 1, 1. So this is the projection of 1, 1, 1 onto S. Therefore, the distance, this is the distance from 1, 1, 1 to S, which is given by that vector V minus projection of S up to V. So basically norm of this to 1, 1, 1 minus 2 by 3, 4 by 3, 2 by 3. So if you calculate, what you will get? 1 by 3 square root 1 by 9 plus 1 by 9 plus 1 by 9. So square root 3 by 1 by 3. So this is the distance from 1 1 1 to S. Now what we have to find? We have to find 3d square. So this is d. So therefore, 3d square will be 3 times this is d square is 1 by 3, 1. So the answer is 1. So then 3d square is 1. Okay. Okay, any questions or doubt? One by 3, 1. Okay, if there is no question, let's move to the next one. so let's start. Today we'll solve Gate 2018 question. This is a question from real analysis. It is question number 16. So let I be the interval close to open 3 and let J be the set of all rational numbers in the interval 4, 6. And K be the Cantor ternary set and L is this set L7 plus X or X is in Cantor set. Then the Lebesgue measure of the set I union J union L is that you have to find. Okay, so this is the NPTEL reference. This you can look into it. Okay, now let's start solving this one. Okay, so I is this set close to open 3 and J is this means rational numbers in the interval 4, 6. Now K is the Cantor ternary set. So what is the Cantor ternary set? So this is there is a construction means how Cantor set can be constructed. So first take the close 0, 1. So this is the interval close 0, 1. So let me denote it by C0. So this is close 0, 1. And we write it by 0 to 1 by 3. We take this point 1 by 3 and 2 by 3 and 1. So in the first step, what we will do? We will first remove this open interval 1 by 3 to 2 by 3. So first remove this interval open 1 by 3 to 2 by 3. Then what you will get? So you will get it. So only remain this interval and this closed interval. So this is from 0 to 1 by 3 and 1 is from 2 by 3 to 1 by 1. So C1, this we call it by C1. So C1 is union of these two closed set. 0 to 1 by 3 union 2 by 3 to 1. Note that each of these has length 1 by 3. So basically C1 is union, disjoint union of two closed interval of each of length 1 by 3. Now again write it means write 0, 1 by 9, 2 by 9. This is 3 by 9, it's 1 by 3. Here it will be 4 by 9. Here it will be 5 by 9. It's 6 by 9, 2 by 3. 7 by 9, 8 by 9, it's 9 by 9 is 1. So in the next step, what you will do? You will remove these two open interval. 1 by 9 to 2 by 9 and 7 by 9 to 8 by 9. Then we call it what you will get. So basically you will get 0 to 1 by 9 this closed interval union 2 by 9 to 1 by 3, 2 by 3 to 7 by 9 and 8 by 9 to 1. So this we call it by C2. So C2 is the union of these four closed interval 0 to 1 by 9, 2 by 9 to 1 by 3, 2 by 3 to 7 by 9 and 8 by 9 to 1. So in this time what you will get? So in the second step we will get 4 closed interval each of length 1 by 9. So do you find the pattern? So in the first interval you will remove you will get 2 closed set each of length 1 by 3. In the next second step you will get 4 closed set each of length 1 by 9. So basically, so continue this process. So what you will get? You will get C0, second step C1 is a subset of C0, C2 like this CK subset of CK plus 1 and dot. So in this process, at the end what you will get? That set is called the Cantor set. So in the limit set, so means Cantor set is basically C, we denote it, which is the intersection of K equals to 1 to infinity of CKs. Right. Note that why this Cantor set is non-empty, because note that each steps 0, 1, these endpoints are always in the Cantor set. these endpoints are in the Cantor set. So C is non-empty. Also, one important property that C is each step it has a closed set. C1, these are the union of these two finite union of closed sets. So each are CK, C1, C2, CK, these are all closed set. And CU defined to be the intersection of closed set. So there is a result that intersection of closed sets are closed. So each CKs are closed, so therefore C is closed because this is the intersection of closed sets. And also where C lies, because C is this all are subset of 0, 1. So C is also lies inside 0, 1. So therefore C is bounded. So in R, this is a subset of R. This is closed and bounded, means C is compact. So we get that Cantor set is compact. Also, there is one important property that one can check that C, one can show that this is uncountable set. This set is uncountable. What you will get at the limit process. Now, but here what we will need, we have to find the measure of this Cantor set because we need to find the measure of this. So you have to find what will be the measure of the Cantor set. This So first note what is the kth stage, what you will get CK, that I have already mentioned the pattern. That CK is that this is disjoint union of 2k closed sets, each of length 3 to the power minus k, right? Because on the first stage C1, it is the union of 2 closed sets, each of length 1 by 3. Now second step C2 is disjoint union of 4 closed sets, each of length 1 by 9, like this. So in the CK stage, you will find that this is CK is disjoint union of 2k closed set, each of length 1 by 3 to the power k. So CK basically disjoint union of 2k closed set, each of length 3 to the power minus k. So what is the outer measure of CK? This is basically infimum of summation of all the measure of this disjoint union. You can cover it by open intervals. So outer measure of CK, this will be less than the length of this set. So obviously it is 2 to the power k closed set, each of length 3 to the power k. So which is 2 by 3 all to the power k. And this is true for all k bigger than 1. So therefore outer measure of C, because C is the intersection of all CK, so this will be less than outer measure of CK. And this is also true for all k bigger than 1. So therefore outer measure of the Cantor set is less than what you will get, because this is less than 2 by 3 to the power k. So outer measure of C is less than 2 by 3 all to the power k for all k bigger than 1. So what is the meaning of this? Left hand side is independent k and this is true for all k. So we can take k tends to infinity. As this number is less than 1, so as k tends to infinity, this will goes to 0. So we get outer measure of the Cantor set is 0. Right. So outer measure, so there is one result that if outer measure of a means Lebesgue outer measure of a set is 0, then the set is Lebesgue measurable and the Lebesgue measure of that set is 0. Okay, so here I forgot that here the set is Cantor set is denoted by k, so that's why I'm writing it C equals to k. So we get that Cantor set is Lebesgue measurable and the Lebesgue measure of the Cantor set is 0. Okay, so you have got the Lebesgue measure of the Cantor set. But here we need to find the L, which is the translate of k. So that we have to find the measure of that set. So let's find this one. So L is the 7 plus x, or x is in the Cantor set. So this is one result from the measure theory, that Lebesgue measure is translation invariant. Means take the any set and measure it, and if you translate it by any real number, and again if you measure it, it will be the same, it will give the same measure. Means under translation, measure is invariant, measure will not change of that set. So this is mean the Lebesgue measure is translation invariant. So we'll use this. So what is L? L is basically you can write 7 plus k because it's translate of k by 7. So by the above result, that measure of L is same as measure of k because this is the translate of k, L is translate of k. And what is the measure of k? That we got earlier, that measure of the Cantor set is 0. So measure of L is also 0. Okay, so we get measure of L is 0. Now we have to find the measure of I. I is the interval 2, 3. What is the measure? Measure of that interval, because this is measurable. You can show that this type of intervals are measurable. And measure of this set is basically, if it's this kind of set, it will be 3 minus 2. So 3 minus 2, it's 1. So length of that interval. So you get measure of close to open 3 is 1. Now only remain the J set. J is all the rationals intersection 4, 6. So this is because Q is countable, it is countable set. There is one result that countable set as Lebesgue measurable and it has measure 0. So that you can also use. So here let me give a short proof of this. So Q is countable, so you can enumerate it. So write it by like this. Q intersection 4, 6, so enumerate it Q1, Q2 like this. So ordered Q like this. Now we want to find the outer measure of this set. So basically you have to cover it by open sets. So fix epsilon positive and take the open cover of this. Means each rationals we take the small open set of length, means qy minus epsilon by 2 to the power I and qy plus epsilon by 2 to the power. So this is open set, and this is at each point we have taken this kind of open sets. So this will certainly cover Q. So take open cover this of Q of this set Q intersection 4, 6. So therefore measure of that set basically, so outer measure of that set, let me write, is less than equals to, because subadditivity of that outer measure, this will be less than sum of this kind of sets. And these are open intervals. What is the length of this open interval? It's 2 epsilon by 2 to the power I. And this is a summable, right? This series is summable. If you calculate the sum, I think you will get 2 epsilon. And this is true for every epsilon positive. So, and because we have epsilon is arbitrary, we can take epsilon tends to 0. So you will get basically outer measure of this set Q intersection 4, 6 is 0. So as this is again the same result, basically J is this set. If this set has outer measure 0, so it is measurable, and measure of that set is 0. So we get all the measure of all three sets. Measure of I is 1, measure of L is 0, measure of J is 0. Now I have to find the measure of the union of these three sets. So let's see where these three sets are lies in the real line. So first in the real line I am writing it 0 to 9. So K Cantor set, this is a subset of 0, 1, right? Cantor set by the construction. So Cantor set lies in here. And I is the interval 2, 3, so I lies in this here. And J is all the rationals in 4, 6. So J is a subset of this set. And what is L? L is the translate of K by 7. So L is a subset, L lies here. Because L is a subset of this set. So from here you can see that I, J and L are disjoint. Yeah, so this is this you will notice. So this you can also check that these three sets are disjoints. So as we get these three sets are disjoint, so Lebesgue measure has a additivity property, finite additivity or countable additivity, that if you get disjoint sets, then Lebesgue measure of union of that disjoint sets are add up. So basically, Lebesgue measure of I union G union L will be Lebesgue measure of I plus Lebesgue measure of J plus Lebesgue measure of L. And we already computed Lebesgue measure of these three sets. Lebesgue measure of I is 1, Lebesgue measure of J is 0, and Lebesgue measure of L is 0. So we get Lebesgue measure of the union is 1. So we get the measure of union of these three sets is 1. So therefore the answer is 1. Okay. Okay, any doubt or any questions? So therefore the answer is Okay, if there is no doubt, then if there is still time, let's solve another question. Okay, so let's start. So today we'll solve Gate 2017 question. This is a question from functional analysis. It is a question number 13. So what it is saying? Consider the non-linear space. Consider the non-linear space R2 equipped with the norm given by this norm. So this is a L1 norm. And the subspace is given by x equals to y. And let f be a linear functional on x given by f of xy equals to 3x. If g of xy equals to alpha x plus beta y for alpha beta in R is a Harmonic extension of f on R2, then alpha minus beta equals to, we have to find. Okay. So this is the NPTEL reference. This you can look into it. Okay, now let's solve this one. So what this is, subspace is given of a means vector space R2 of, and so it is saying that, so let me write. So R2 is equipped with this norm x, y, let me call it, let me write it this, where the norm is, it's mod x plus mod y. So this is sometimes also called L1 norm. And what else is given? X is a subspace is given. X is a subspace of R2, all xy in R2 such that x equals to y. So this is a diagonal subspace. So let me write. So suppose this is x, this direction is y, so then this line is x equals to y. So this is the subspace x. This is 0, 0. And f be a linear functional. Let f be a linear functional on x given by f of xy equals to 3x. So basically x here y equals to x. So this is the linear functional on x is given. And what else is saying? Let g of xy equals to alpha x plus beta be the Harmonic extension of, is a Harmonic extension of f of R2. So let g of xy equals to alpha x plus beta y for alpha beta in R is a Harmonic extension of f on R2. So if what is Harmonic extension? It is saying that Harmonic extension is basically saying that if a functional which is defined on a subspace, then you can extend it to a whole, that vector space, whole vector space, without extending the norm, means with norm preserving extension. So Harmonic is saying that means from Harmonic extension we got as, means G is a Harmonic extension of f, Banach extension of F. So we have two property. First one, what we have? G, if we restrict it to X, it will be same as F. And second one, so norm of G, so this is our whole vector space R2, let me denote it, and norm of F over X should be the same. So these two Banach extension tells that you can extend the linear functional F to a whole linear functional on R2, which is G, given by G, with preserving the norm. Okay, so we have to calculate the G basically. So let's calculate G. So from the condition 1, what we will get? So from condition 1, what you will get? That G of xy restricted to F, you will get F of xy, or what you will get? Alpha x plus, so on x is beta x, right? And this side it's 3x, as xy in x imply x equals to y. So you get alpha plus beta x equals to 3x. So this is for all x in R. So therefore you will get alpha plus beta equals to 3. So you get one condition on alpha and beta. Now from 2 we have to deduce another condition, and from there we have to solve alpha and beta. Okay. So for that we need to compute the norm of F and norm of G. So let's calculate the norm of F and norm of G. So what is norm of F? So norm of F on X means, so it means this is a functional norm, means supremum of norm of xy. This should be less than 1 such that F of xy, where this xy is in is x, right? Now what is this? So xy is norm of xy, so this is, if you write it, so it is supremum over, this is mod x, and as xy, so it is again mod x, so this is less than 1, or you will get 2 mod x is less than 1, or mod x is less than half. So you will get this condition. So supremum over mod x less than half, and this is 3x. So means this is less than, so this is less than, what you will get? 3 times mod x, which is less than, so let me write, which is less than 3 by 2, because mod x is less than half. So you get norm of F is less than 3 by 2, but we need exactly. So let's find a point for which the norm will attend. So let's take which point? Let's take this point. Take half comma half. So as x equals to y, so this belongs to x. And what will be f of half comma half? So this is 3x. So if you put 3 into half, it's 3 by 2. So at 1 comma 1, the f will take the value 3 by 2. So the supremum is attained at the point 1 comma 1. So norm of f is 3 by 2. Therefore, norm of f on x is 3 by 2. So you get the norm of f. Now you have to calculate the norm of g, and then we have to equate these two. So what will be the norm of g? So note, now we have to calculate norm of G on R2. R2 with which inner product? That norm. So basically this is a linear functional, right? So what is the dual of this? So G is a linear functional on R2. So note that. So this is a well-known result. It is known that dual of, so this is a dual R2 with L infinity norm, suppose take, and it's take dual, means all linear functional on this space, which is isomorphic. R2 with L1 means all linear functional on this space. So this is isomorphic to R2 with L infinity norm. So what this is saying, and this is isometrically isomorphic. And basically the map for any given psi here, if you map it to psi of first basis vector E1 and psi of E2, this map will give the isometric isomorphism, right? So this map gives the isometric isomorphism. So with using this one we can compute the norm of G. Means here what it is saying, that psi here the L1 norm, means in the dual norm, which is same as this maximum of psi E1 comma psi E2. So therefore similarly G is in the dual of this, right? So therefore as G belongs to R2 with this dual, so basically this norm is the L1 norm. So dual where this norm is the L1 norm. Which is the L1 norm. So norm of G will be, so by the above observation, norm of G will be maximum of GE1 comma GE2. And what is GE1? GE1 what is? So G is alpha, E1 is 1 plus beta dot 0 is alpha, and G of E2 is alpha dot 0 plus beta dot 1 is beta. So we get norm of G is maximum of mod alpha comma mod beta. So now we get, so this is a norm on, so now we get both the norm. Here we get the norm of G is this, and norm of F we earlier get this. And by the condition 2 it is saying that norm, both these norms will be same. So by 2 we get norm of G is same as norm of F, which implies maximum of mod alpha comma mod beta is 3 by 2. So let me call it true, and we get earlier one condition. From the condition 1, this is 1. So we get two conditions, 1 and 2. So we have to solve these two. Therefore we get alpha plus beta equals to 3 by 2. This is condition 1. And maximum of mod alpha mod beta is 3 by 2. Now we have to solve these two, alpha and beta. What will be the possible values of alpha and beta? So note, can alpha and beta both be negative? Note, alpha and beta both can't be negative. If both are negative, then the sum will be negative, so it will not satisfy the first one. Right? So both cannot be negative. So can one be negative? Suppose alpha is negative and beta is positive. Then what will happen? So note that if alpha is negative and beta is positive, then the sum is positive. Means one number should be, suppose it is non-zero also, assume. Right. So suppose one is, alpha is 0, then beta is 3 by 2 you will get. And so suppose, assume first both are non-zero, then what will happen? So if alpha is non-zero, then if it is negative, then the sum will increase, because then the one should, suppose let's say if alpha is negative something, then as alpha plus beta is 3 by 2, then the beta should be bigger than 3 by 2, which will contradict the maximum of these two will be mod of these two is 3 by 2. So also one cannot be negative also. So both should be positive. So either alpha or beta cannot be negative. Right. So both should be non-negative. Now what are the possible values? So suppose 1 is 0, alpha is 0, then what will happen? If alpha is 0, then what will happen? Then the G, what you will get, is basically beta y. Then if alpha is 0, then beta will be 3 by 2. So basically you will get yeah, there are possible values. That means if 1 is 0, then the extension will be, what will be the extension? Means there is no it's not a non-trivial extension. It is the same as f, right? Because 1 will be 0 and on x equals to y it is same. So it is not a non-trivial extension. So both, if 1 is 0, it is not a non-trivial extension. So both should be positive. So as it is a non-trivial Harmanek extension, so it is a both are positives. As G is non-trivial Harmanek extension, so alpha, beta both are positive. Now what will be the possible values? So as sum of both the because maximum of now 1 can be 0, right? Can 1 be 0? If both are same, no, I think what is the sum we have got? Oh, I forgot. This sum is 3. That's why I am getting confused. This sum is 3. This sum is 3. So what will be the possible values of alpha and beta? So therefore, alpha equals to beta equals to 3 by 2. Yeah, also alpha beta can't be 0, right? From here, if alpha is 0, then beta, so alpha beta can't be 0 also. Also, from this alpha or beta cannot be 0. So the only possibility is alpha equals to beta equals to 3 by 2. Then what do we need to find? We need to find alpha minus beta. Then alpha minus beta will be 3 by 2 minus 3 by 2, it's 0. So what will be the answer? The answer will be 0. Okay. Okay, any doubt from this one? What you have just solved? Or any questions? I will upload the notes also. No questions? So this type of, yeah, means it's often you have to, this harmonic extension may not be unique. So that's why it is saying that if G is a harmonic extension, there may be many harmonic extension. Means this you have solved here. You get here, you can see that here you get what it is unique, only one alpha and beta exactly. There may, in order to, means it's not necessary that you can exactly solve by unique solution. There may be many harmonic extension. I think there is some necessary condition when the harmonic extension is unique. Strict convexity is needed. No doubts? Okay. So if that is no doubt, Yeah, then we can stop. Today is the last day of this NPTEL GATE. Yeah, you can find all these lectures in the GATE NPTEL portal. Also the, I think, yeah, in the also there you will find also the recordings, and I will share also the notes. Okay, so let's end this session then. Okay, so let's stop.